Okay, let's have a look here. So, close those up. I want to show, let's go through a centripetal force problem using a free body diagram. Then I'll let you work on this stuff because I want you to try some of these out. All right, so we were looking at the example with the car, right? The car was driving on the left side of the board. We'll divide this up. The left side of the board over here, this is a ground view, right? The car is driving into the board, going around in a circle. Here's the bird's eye view. This was our axis of symmetry, or axis of revolution, we could say. And here's the axis of rev right there. And there's our car traveling in a circle. Okay, so we got two forces here. You told me that there was going to be a normal force pushing up and a weight pushing down. Okay, Seth, what's the other force acting?
Friction.
Friction, right? If there weren't friction, the car would just zoom off tangentially in a straight line. It couldn't turn, but when you introduce friction, it can make the circle if it's enough friction, right? So we've got this other force that's acting, let's see, it's going to be orange, I guess. So the other force is then acting towards the center of the circle. That's our frictional force. Static or kinetic?
Kinetic.
How come?
Because the car's moving.
Okay, but what is
Static because the point's not.
Okay, it's static because the surfaces are not sliding, right? A point on the tire doesn't slide relative to the road, so it's static. Okay, make sense? So then here it is on this graph, right? Okay, everybody agree? Okay, so there's our free body diagram, right? So we're going to take this free body diagram and we're going to write out the equations of motion, just like before, right? This all should look pretty familiar. Okay, so let's write out the vertical equation of motion. So the y component of the net force is going to be what? What do we get? Okay, normal force is our positive contributor minus mg, and what do they sum to? Zero, because there's no vertical acceleration. Okay. Now, what about the other equation of motion? We used to talk about the, like the x and y components for parallel and perpendicular. But this time, what do you suppose we're going to call the direction of this force? R would make sense, yeah. We're going to call it centripetal, okay, because this is uniform circular motion. And so the force that's causing this thing to move towards the center is the centripetal force. And what is that? F sub s. It's static friction. Okay, so then you see that centripetal force, it's once again, it's not a specific force, it's just a category of forces, right? So in this case, it's the sum of all the forces that are contributing to the circular motion. There's only one this time, right? Okay, so that's equal to what? Say it again. True, okay. Yeah, what's it equal to, though? What does the net centripetal force add up to? The second law? Is it zero, though? Because if it was zero, it's got to be mass times acceleration, right? So it's going to be m times a sub c, because it's the centripetal acceleration, right? So it's the same concept we've used before, but we're just going to adapt it to uniform circular motion. And so what are we even trying to answer here? What's mu sub s, okay? Well, then all we've got to do now, I mean, this, from here on out, it's pretty straightforward, right? We know from the first equation, if we solve for normal force just equals mg, and we know that F sub s is just mu sub s times normal force. But what's normal force? Mg, right? So we end up with mu sub s mg equals m times centripetal acceleration. I could divide each side by m, and what's our centripetal acceleration equal to?
mu sub s
Times g, sure. So then if we want to solve for mu sub s is equal to a over g, right? Which is, okay, how are we going to find what a is? B squared over r. Yeah, right? It's like the kinematics of the situation in a way, isn't it, right? Because if we're traveling in a circle with a radius of 56.8 going that fast, there is only one centripetal acceleration that's going to cause that, right? Because it's uniform circular motion. So we could calculate A, and we're going to go back, and we're going to go back to this equation in a second. I've got a little question for you. But if we calculate A, what was B again? It was 32.3 over 56.8, was it? So what's that roughly equal to?
.4.
18.4-ish. Keep it in your calculator, right? Meters per second squared. And so if we plug that in up here, what do we end up with? We end up with mu sub s equals, what is that divided by 9.8? Rounded to how many places? 3 places.
1.87.
Say it again?
1.87.
1.87? Oh, that's pretty big. 18.4.
Yeah, I have 17.74.
32.3 meters per second.
All of my answers were above 1.
Okay, well, it could be. I mean, that's possible. The tires can be really, really sticky. I mean, they could actually be, you can have coefficients bigger than 1. That seems a little unrealistic, but, I mean, that's just the way I programmed it. There's going to be some variability. I mean, really the main thing is, can you find the number? So what was it, 1.87? Okay, my question is, I should probably tweak those so they don't give those kinds of answers, but is it equal to? It's approximately, sure, but let's just even say that
Greater than or equal
it's got to be greater than or equal to, right? The coefficient of static friction has to be at least that, but it could be greater, right? Think about this example. If I'm going to push this, with 1 Newton, what's the maximum static frictional force? Well, it's greater than 1 Newton because it's greater than or equal to 1 Newton because it's not moving. Okay, I can prove that it's greater than 1 Newton because now if I push with 2 Newtons, it still doesn't go anywhere, right? See what I'm saying? So the static frictional force just has to be at least that big. The coefficient has to be at least that big. It might be bigger, right? But it has to be at least that big. Well, we could say if we wanted to get a single answer, we could say what would the minimum value of the static coefficient be? Static coefficient of friction be? Well, that's the minimum it could be, right? Might be bigger. Okay? Yes, sir.
So like the one I was just doing, it's the same thing but finding tension instead of
Right.
friction. Is it the nothing
So it's
changed?
easier in a way because you don't have to do, slightly easier.
Yeah.
Yeah. Yes, ma'am.
How do you do it with an angle and a frictional
Okay. Yeah, so let's look at something else here. Let's look at, let's give ourselves a little challenge here. Let's say that we want to drive a car around a corner in conditions that might be limit our traction. So there might be some inclement weather coming. We want to be able to design a freeway so that cars could travel at reduced speeds in really bad conditions and not slide off the road. Okay, so let's say, does that make sense? So let's say we want to do, we want to have cars go around a turn with a radius of 100 meters, okay? And we might have coefficients as low, friction as low as 0.12. Okay, I'm just making this up. This would be kind of a cool problem to do. We want to figure out what can we do to that road so that we could, you know, we could design the road in such a way that cars wouldn't slide off. If they're gonna be traveling at speeds of up to, let's say, 40 miles an hour. Okay, we expect there might be cars going as much as 40 miles an hour, even if it's bad conditions like that, okay? So let's summarize all that stuff. So what did we say? 100-meter radius of the turn equals 100 meters exactly, let's say. We said the coefficient of static friction might be as low as, what did I say, 0.12? 0.12? Make it 3 sig-figs, how about? And then the speed would be 40 miles per hour, so we gotta convert that to meters per second. So let's see, we're gonna say, here's the only way I know how to do miles and meters. I just say, I know that a 10K race is 6.2 miles. So we do 6.2 miles for 10,000 meters. That's how I always remember it. I mean, it's close enough for us, I suppose, huh? And then hours to seconds. 1 hour is how many seconds?
60 times 60. 3,600.
3,600, there you go. So now we end up with what? What is that? So 40,000 divided by 36, so that's gonna be,
The 40,000 divided by 360.
yeah, it should be 40,000, oh no, 400,000, you're right. 400,000 divided by the quantity 6.2 times 3,600. What's that give us? About?
17.9, does that sound right?
That sounds about right. So there's our speed, okay? So let's figure out then, how would we approach this? Good engineering problem. How would we approach this? So we got cars going around this corner, right, on the road. Here's the center of the turn. How might you approach this? Yeah, we're maybe gonna have to bank the turn, right? That's probably the only way we're gonna be able to accomplish this. But in order to figure out what the banking angle should be, what could we do? And what's gonna be the critical factor here? We want the cars to be able to make the turn, right? Agreed? So how are we gonna, what's that mean in terms of physics?
The friction between the car and the road is great enough that the car doesn't slide off.
Okay, so will the combination of friction and maybe some other component of the centripetal acceleration or centripetal force would be enough, right, so that it's going to be able to make the turn? Agreed? Okay. So then we have to specify the appropriate centripetal acceleration to make the turn. Now that's independent of what we're going to do, right? That's really only a product of centripetal acceleration is only going to be a product of what our R and our V are, right? Not specifically a product, but I mean the outcome is going to be based exclusively on V and R because centripetal acceleration is just V squared over R, right? So that stuff tells us that the minimum, that we have to be able to generate a centripetal acceleration of what? That's going to be V squared, so what's 17.9 squared divided by 100? 17.9 squared over 100. 3.204?
Yeah.
Boy, that's pretty big. Are you sure?
Yeah.
Okay, I guess our radius needs to be a lot bigger than that. Is that right? Yeah.
Yeah.
Seems, I guess that is a pretty small radius for a road. Radius of curvature. Let's make it, instead, let's make it a 200 meter. Needs to be probably even bigger than that. Oh, no, we're just talking about centripetal acceleration, sorry. I was thinking coefficient. We're okay. So what is it then again?
3.204.
So we'll say 3.20 meters per second squared needs to be our centripetal acceleration. Okay, so then let's see, first of all, I mean, is the static friction going to give us enough? Right? We can check and see. So we just did all the work on this. You guys have this down in your notes, somebody? So, because I'm going to leave this page, we're going to need that information. So if we go back to this, we did all the work right here for a similar problem. We've got the centripetal acceleration. Well, we could just do it in the way we did the last one. We could see what would our coefficient of static friction need to be in order to make that turn. And we'll see if 0.12 is enough. So if we plug into this equation right here, mu sub s equals centripetal acceleration divided by g, what do we get? 3.20 divided by 9.8. Not enough, is it? That's going to be around 0.3-ish. We only get 0.12 for our assumed inclement weather static coefficient, right? So it's not enough. So we have to bank this road a little bit, don't we? Okay, so how could we look at that? Let's go back to a picture like this one. And we want to set up, here's our model, where if we're driving into the board, we're going to bank the road up at some angle theta. Everybody agree? Okay. And if we draw a free body diagram, what are the forces acting on this car? So we're going into the board, and the center of curvature is over here somewhere, right? What are the forces acting?
Normal force of gravity.
Okay, so we've got normal force. Whoops, sorry, gravity. I mean gravity. Normal force is acting how? Up. Okay. What else?
There's the centripetal force going towards that.
Okay, but remember, the centripetal force is not a specific force. It's just going to be an umbrella. It's just going to be a net force, right? So there is one other force acting presumably here. Friction, okay. And in what direction is friction going to be acting this time?
Straight out.
It's going to be,
Or inward, I mean, but
it's going to be, actually it's going to be pulling us down, isn't it? Right? It's trying, because our car, what we want to do is we want to minimize this angle and make it as, the banking angle as small as possible, right? Because extreme banking angles aren't good, right? If it's too severe, then what if your car breaks down? That's just inconvenient, right? Plus they're harder to build. They're more prone to erosion, and we don't really want to do that. It's just weird. You don't see many roads that are extremely banked, right? So we want to make this thing as small as possible so that the banking angle coupled with our minimal friction is going to be enough to keep the car on the road, right? Okay, so we know that the friction is going to contribute to the centripetal force, but it's not going to be enough, right? That we didn't have enough. So there's our static friction. Okay? Make sense? Okay, so let's set this thing up then so that we can, we got to set this thing up so we can figure out what the centripetal force is. Okay? Now this time, normally, we would have set this up so that we used a parallel and perpendicular components of the force. Does that make sense? Right? Why is that maybe not the best idea here? In fact, why is it not going to work here? What does one of our components have to be if we're in uniform circular motion? It's got to be centripetal, right? And so if this is, let's just say that this is the axis of revolution right here, well then the centripetal force has to act directly, right, has to be perpendicular to the line connecting the point to the axis of revolution, has to be perpendicular to that axis, and the centripetal force has to act, it's acting in the direction directly towards the center of the circle. It can't act at an angle, right? It's got to act straight towards the center. Okay, so what we've got to do this time is unfortunately, we've got to break these two vectors up into components that are acting centripetally and non-centripetally, right, and vertically. Okay, so let's do that. So we've got, does that part make sense? Okay, and this is, by the way, I'm not going to ask you to do anything this hard, but this is a pretty cool question that we can actually do. I mean, we can do some engineering here. This is a little tougher than what we're going to do this year, but in the future, you'll be doing stuff like this, right? And this will make sense to you. I know it will. So let's break these up into components. So if that's the angle theta, which angle there? Well, actually, pretty obvious. That's going to be theta, isn't it? Right there. Okay, so that's theta, and that's theta, right? So if we want to orthogonalize this free body diagram, then here's the body. What are the forces acting? Well, mg still acts vertically. What are going to be the components of normal force? So we're going to get a vertical component of normal force, which is what? It's going to be a cosine issue, isn't it, right? Because the vertical component's going to be adjacent to the angle, right? And what we're really going to do is we're going to break this up into a vertical component and a horizontal component that are at right angles, right? So we get normal force times cosine theta, right? And then we're going to get another component towards the center, which is going to be normal force sine theta, right? What about friction? Friction is going to break up into a horizontal component, cosine or sine? Cosine, right, because it's adjacent, and a vertical component. So let's add those. So we're going to get F cosine theta, and a little bit going down, F sine theta, right? Make sense? Okay. So, what do our equations of motion say then? How about the y component?
F1 cosine theta
Minus
minus mg.
mg minus, it's supposed to be friction, this is supposed to be lowercase. So friction times sine theta, okay? What about in the centripetal direction?
Just defend sine theta plus friction cosine theta.
Plus. Okay?
And up top, mg should be added to f sine.
What did I do?
Should be
What did I forget?
fn cosine theta minus mg plus friction sine theta. Right?
No, you subtracted.
Oh, that, okay.
Right, because it's going down. Yeah. Okay. Okay, so now what's the stuff that we know and the stuff that we don't know? So we're trying to solve for theta, right? We got to be able to somehow get rid of everything else. So what can we do? A, we can calculate, right? Because we know what V in fact, there's our A right there, isn't it? Make sense? Okay, so we've already calculated what the centripetal acceleration needs to be. Mg, we know. I mean, we could, if we need to, the m's really ought to cancel. they really need to cancel here somewhere. I'm sure they will, because it just doesn't seem like it should be dependent on the mass. So I'm sure they'll cancel. If we need to, we can specify that, but I don't think we will. And then the coefficient of friction we're given, right? So we should be able to find out what F is. Okay, what's the other unknown up here right now that we don't have an answer for? If you look at these two equations right here, we don't know theta, and what else don't we know? Yeah, normal force, right? We don't know, and normal force is gonna, who knows what that's gonna be, because look at the normal force. The normal force, it's not just equal to mg this time, is it, right? But we have two equations, and so we ought to be able to substitute, right? So what can we do? Maybe use that top equation, because that's equal to 0, right?
Solve for F of n.
Yeah, we could solve for F sub n, right? We could isolate that. So what's that going to give us in this first equation? So if I isolate F sub n, I could add those terms to the other side, right? What about our friction, though? We got to do one more thing. Boy, I've never done this problem before with the group. This is pretty tough, right? We're not giving up. We can do this. We got to write friction in terms of normal force, though, don't we? Right? Because friction equals mu times normal force. So let's call this equation 1 and that equation 2. Let's rewrite these one more time. Whoops. This is probably this might be the hardest problem we've ever done in the physics class. It's pretty good. It's pretty hard. Okay, so if we plug in our definition for friction, right, static friction, it's just mu times normal force, and we do know mu, right? So if we make that substitution, then don't these equations become, so 1 prime is just going to be normal force cosine theta minus mg minus F is going to be mu times normal force times sine theta equals 0, right? And the bottom equation is going to become 2 prime is going to be normal force sine theta plus F. Well, that's just mu times normal force cosine theta equals m a sub c. Okay, so if we're going to solve for normal force in that first one, what do we have to do to solve for normal force?
Move mg over.
Move the mg over. Okay, good. So we'll add the mg over to this side. So we get normal force cosine theta minus mu normal force sine theta equals mg. Now what? Factor out a normal force, right? This ought to look a lot like some stuff we've done in calculus this year, right? When we're solving for like y prime when we're doing implicit differentiation, right? So we're going to factor out the f sub n, and we're left with cosine theta minus mu sine theta. And then we just divide both sides by that, right? So we know that normal force has to equal mg divided by cosine theta minus mu sine theta, right? So what do I do with that? Sub it into the other one, right? Okay, this is going to be we're not going to be able to solve this equation analytically. We're going to have to let technology do it. But we should be able to set up the equation whose solution is going to be our banking angle for our free weight, right? So if we plug that in, then we're going to get that whole quantity. So mg sine theta, if I multiply by sine theta, over cosine theta minus mu sine theta plus mu times cosine theta times this. So over the same thing. Cosine theta minus mu sine theta equals MA. Okay.
Yeah. You can divide by mass and cancel out.
Okay, we could cancel, so good, the masses cancel, knew they had to, right?
And then combine the g sine theta and the mu g cosine theta over cosine theta.
Okay, so we have a common denominator, don't we, right? So this actually looks decent, right? We end up with, I could factor a g out, and what am I left with? Sine theta plus, plus mu cosine theta.
Yeah.
Oh, this is really cool. I like it. Divided by cosine theta minus mu sine theta equals A, centripetal, right? So is there a way, that'd be tough, that'd be really tough. We multiply it by conjugate.
What are we solving for at this point?
Theta.
Oh.
So I don't know that we're gonna be able to, let's just solve this thing numerically. That's gonna be pretty hard to solve analytically, right? But we can plug in all the numbers now. Mu was 0.12, right? Centripetal acceleration was 3.2, okay, 3.2. So we should be able to plug this in and let technology do our bidding now, right? So we end up with 9.8 times the quantity sine theta plus 0.12 cosine theta over cosine theta minus 0.12 sine theta equals 3.2. Okay, so let's find the solutions of this. So let's graph, how about if we try graphing it on Desmos? Oh, this is so cool. This is like a real problem we're doing here. So let's subtract 3.2 to the other side, and we'll write this function and find the zeros. Okay, and we'll do it we're going to be in radians mode, let's say. So let me go to radians mode. Where do I do that? You guys know where to do that?
Yeah, go in the settings button.
The
You
wrench right there.
Yeah. You're
Where does it say radians? Oh, bottom. Okay, gotcha. Good. Okay, so then let's just put this whole thing in. So it's going to look like, oh, darn it. It's going to look like, oh, darn it. Come on. So we get 9.8 times the quantity sine theta, I'll call it sine x, plus 0.12 times cosine x. Okay, all that divided by cosine x minus 0.12 times sine x, and then minus 3.2.
Oh, wow.
Will it do it?
Oh, yeah. Oh, wow.
Okay,
What did we solve?
so we get something relatively crazy, but that's all right. We're just going to zoom in, and we're looking for that answer right there, aren't we?
0.2.
So it's 0.1962 radians.
How'd you know that?
Huh? Because, yeah, see, he went to 0.5. He just, it's not that hard.
Nothing to
So it's just not
He just
that
did it all in his head. It's no big deal. So 0.1962, let's convert that into degrees. See what we get. So our conversion, right?
Sad. I understand you.
What do we multiply by to go to degrees? What's that give us?
Uh, 11.2.
Okay. That seems about right, doesn't it? You think about that. Think about that in terms of, that's pretty cool. That's what it would take. That would be where you could, so with that coefficient of friction traveling at 40 miles an hour, you could just make that turn, right? With a minimal, with 0.12 coefficient of static friction, right? So if we were to look at that, let's see, let's go Y, X, so we can visualize that. So if we're looking into the road, that's going to be at about, wouldn't you say, 11 degrees, so that's 45, 22 and a half, so it's down about, something like that-ish, don't you think? That seems about right. Pretty cool. Okay, yes, sir.
So if the bank is any lower than that, any more flat, you probably just lose grip.
Yeah, right, so if it were, that would be the minimum banking angle, right? So if it were lower than that, either you'd have to reduce your speed more or have more traction in order to be able to make that turn. And that's, honestly, that is how they do it. That's how engineers would calculate how to bank a road, is they would say, you make an estimate of worst case conditions, and then you don't want to slide, so if it's really icy, you don't want to make it too steep, or you slide down the hill, right? But assuming, right, so it's,
So how does mass not factor into that? Because wouldn't it affect it differently if the little car was going over besides the semis?
no, it wouldn't, because remember, here, I can defend this. Remember how we looked in the lab when we pulled those friction blocks with the little caliper? It didn't matter whether we had the big surface down or if it was, right? It doesn't make any difference. If I'm pushing on a block and it's got that surface down, or the big surface down, or the little surface down, the frictional force is the same either way, right? How come? Think about our discussion we had way long time ago about what friction is. It's the little knobbies interacting with each other, right? If you got a bigger surface area, that makes a smaller pressure, right? Because pressure is force per unit area. The weight's the same. So if you have less pressure, the knobbies get pushed together less forcefully, but there's more knobbies interacting, right? If I take a smaller area, then I have greater pressure, so some more significant interaction. The micro welds are stronger, but you don't have as many of them, and it exactly balances out, so it doesn't make any difference, right? So it doesn't, okay, so point being that if you're traveling around this turn and you have more mass, you're going to create more friction, right? But you need a commensurately larger centripetal force, which it just gives you, right? Same thing we found, would you agree that if you were sliding around, those water parks where you slide around that, it's like a little funnel thing? Watch people on there, it doesn't matter how much they weigh, they travel the same path, right? Because there's almost no friction in that case, it's just gravity. And what's going on? Well, if you're heavier, then you get a larger centripetal force forcing you to make the turn, right? If you're lighter, you don't get as much centripetal force, but you don't need as much, right? And so it doesn't make any difference. If you took two planets, if Jupiter were moved into Earth's trajectory around the sun and it had the same speed as Earth, it would travel the same path, okay? So it doesn't, mass isn't an issue here. And if you think about it, it really shouldn't be. If you take cars going around that turn at the same speed, they should all be able to make the turn regardless of their weight, right? Now it is going to be compounded if, probably trucks would have, I don't know, shouldn't make any difference.
Because they always have, different speed limits for trucks.
Yeah, but
Is that mainly just because they're top heavy?
it's because they're top heavy and because they're harder to maneuver, and it's, they're just, if they get in an accident, it's a worse accident.
Yeah.
It's gonna kill somebody if it's a truck, because they're so big, but, yeah. All right, so the question you're asked is not that hard. So let's just look at the one on Moodle, the two on Moodle that you're gonna, one of them's pretty tricky. One of them is rather challenging, and it's only worth 10 points out of 100.
The difference between A minus and an A plus.
Big.
Let's see here, so, physics.
My mom said you have to stay less than 6% or the car slides on ice.
You have to say what?
Stay less than 6% or the car slides on ice.
For the banking angle? Yeah, and why would that be? Because it's, so if the car stopped, it would slide down the turn, which is what you don't want, exactly. So really, I mean, ours wasn't the same kinds of constraints that engineers would use on a road. What did we say? We said you have to be able to travel at 40 miles an hour around the turn with 0.12. 0.12 is really low. You're almost never going to have a static coefficient of 0.12, especially if your traction tires are required or something. So we picked, I just kind of pulled those out of my head. Those weren't probably what we'd say is something like 0.3, and you'd assume that the speeds would have to be significantly slower if it was that tight a turn, right? But you get the idea. Those are the kinds of calculations that you would do if you were an engineer. Is that what your mom does?
Well, that's what she went to school for. Now she does wastewater treatment plants.
Oh wow! So she was a civil engineer? Oh wow, that's pretty
She
cool.
did roads and
So that's good to know. So 6% is kind of the maximum they would ever let you do, because that's the point where they assume with. So we could figure out. Okay, here's our plan for Monday or something. We got to figure out then if that's what they're saying is the maximum angle, we have to be able to assume what we can easily calculate what the minimum coefficient of friction they're assuming is, right? It would be the one that would just allow a car to stay without slipping on the banking angle, on the. Yeah. Well, you can ask, but we got to figure it out on our own.